So we're going to be talking about chemical reaction rates, factors that affect reactions, rate laws, integrated rate laws, the collision theory, reaction mechanisms, and catalysts. Okay. Some of the things we're going to talk really deep on, and then other things we're just going to kind of like rush over because we're going to give you the bare bones. Okay. Be truthful. Okay, so chemical kinetics is just the measurement of a reaction rate or the speed of a chemical reaction. So often the way that we determine the chemical rate is by the reaction itself, right? So it's done experimentally, right? And so, you know, how often we'll just sometimes describe to kind of keep it simple and not too complex. We'll say, oh, this is a fast reaction. Or, you know, oh, this is a slow reaction. Well, you know, there's actually time that's associated with what we perceive to be a fast reaction and a slow reaction. And so this is the chapter where we're going to be focusing on how do you measure the speed. Yeah. So the speed of a reaction. And then what factors are going to be involved in that measurement. Now, sometimes it is very difficult to actually get the correct kinetics of a chemical reaction. So a lot of times we'll have to extrapolate or just do things, like I said, experimentally to try to figure that out. Okay. And that's going to be really important for us to understand. Okay. So, about that. So like, for instance, if we take a look at a lizard just chilling on the sun, right? We know that lizards are cold-blooded, right? So they actually have to use the sun to help their metabolism speed up. So if it's cool, their metabolism is going to be slowing down. If it's warm, their metabolism speeds up. So, yes, sir. Yeah, probably, yeah, because they want to try to stay warm and stay alive, yeah, and keep their body function working, right? Because then also they eat something and that stuff will just sit in their gut and probably rot because the bacteria will start eating up more of it and then causing issues in their stomach later on. So if we take a look at this, right? So that mechanism of the lizards metabolizing, digesting their food, right? So if it's cool, it's going to take them much longer to sit there and digest their food. But as we increase the temperature, that's going to help speed up reaction. So now this is kind of universal for all types of chemical reactions, right? Regardless of whether it's, you know, a biological reaction or whether it's something that we're doing. Right? The increase in temperature is going to speed up our reaction. Okay, and that's going to be an essential. Yeah. We'll talk more about that later. So when we often define or we're talking about a reaction, we often have to make reference to the temperature that we're going to be doing at, because we know that at higher temperatures, that's going to affect our reaction. Right? So if we're doing things at room temperature, you know, that we often take that into consideration. So if we take a look at the rate of reactions, right, or a chemical reaction rate, that is just going to be that change in a chemical over a given amount of time. So the change in a chemical over a given amount of time. Now, when we're talking about that change of chemicals over a given amount of time, we're talking about the concentration of that chemical, or we're talking about the pressure of that chemical, right? Because that's the things that are going to be changing. So we're going to be looking at the concentration of a particular chemical or the pressure of a particular chemical. Okay. Thank you. So concentration is like the universal, right? You guys remember how to measure concentration? That's all right. That's all right. If it works for you, you know, use it. Okay, so if we're talking about concentration, we're talking about what units typically. What units, when we're talking about concentration, what units are we typically talking about? Concentration. Moles per liter, right? So molarity, right? Okay, so that's typical that where we're making reference to. So we're going to go back to concentration, right? Okay, so so we're also going to express things in what we call a rate expression, right? And that's just a mathematical representation of a rate of the reaction. So if we talk about the mathematical definition of the rate of reaction it's just the change in concentration over change in time, right? CF meaning concentration final minus concentration initial over time final minus time initial. Don't mistake that T for temperature, right? Although we have talked about temperature. It's still going to be a T, but usually we use lowercase t for time. I just kind of screwed up and put a capital T. Let's see. Yeah, I've got to fix it later. So. Okay, so if we look at this chemical reaction where we have ammonium hydroxide, and ammonium hydroxide almost instantaneously turns into ammonia, gas, and water. It's like almost instantaneous. We open the bottle, guess what we have? Ammonia and water. Okay, so now if we looked at the time, right, we looked at it over time. So in other words, since the reaction is going from ammonia hydroxide to ammonia and water, you're going to have minus the change in the ammonium hydroxide over the change in time, or that's going to be equal to the change in ammonia over the time, right? So in other words, it's like what you're losing, you're going to be gaining, right? So that's why the minus is there. And then on the other side, we have it at a plus value. That's what we're gaining. Now, the thing is that since this is a 1-to-1 mole ratio, right? So then we could either be gaining the ammonia, right, in terms of the concentration. And typically we looked at concentration of a solution. We're not looking at water, okay? So, so we're going to be looking at concentrations, not water. So if you have liquid, solids, those guys aren't going to affect our rate. Only the things that are solutions, aqueous, or gases are going to affect our rates. And we'll get to that here in a second, okay? And there's a very specific reason why that's the case. Okay, you guys are good with me so far? Pretty simple, right? Okay, so the rate of reactions are always going to be, the quantitative is going to be a positive value, right? Because if it's reacting, you're going to get a positive value that's going to be associated with it, right? Concentration is often expressed in molarity, which we've already talked about. Okay, so what I'd like you guys to do is, so you saw how I wrote the rate of reaction earlier? Can you guys do the rate of reaction for this reaction here? So we have, so now we're working with gases in this case. So then how would you write this rate of reaction? Okay, guys, help me out here. Okay, so let's start off with the rate of dinitrogen pentaoxide. How would I write that one? Negative delta it's a gas. So am I going to use molarity or am I going to use pressure? That's right. I'm going to use pressure. So P Don't worry, we'll get there. Just relax, just relax. Okay. So if we were trying to relate, and this is the question that she was getting to. So if we were trying to relate the pressure of dimethyl oxide to the other, for them to be equal, we know that we have to take into consideration the molarity. And we know that there's a 2-to-4 ratio between the product, the reactant and the product, right? And so we'd have to take that into consideration. So in that case, what we would do is if we were trying to set them equal to each other, right, then it would be equal to 4/2, and then the pressure of nitrogen dioxide over the time. Okay. Head of the game, right? So, but if we were just talking about the rate of just nitrogen, we would just only have to write it as this. But if we were trying to set them equal to each other, we have to take into consideration the coefficients. Okay. So in case of the nitrogen dioxide, then it would be written the same way. The change, oops, I forgot to change delta. Delta P, no, 2 over delta T, and delta O, oops, PO, PO2 over delta T. And both of those values would be positive down here for the nitrogen dioxide and the oxygen, where it would be a negative, or rate of decomposition, in other words. Okay. Questions, concerns? Cash, relate. Okay. Yes. Yes. Because the ratio, it's for every 2. Yeah. And so if we're just solving, we're saying that the concentration, the loss of this, in respects to the gain of the nitrogen dioxide. Okay. Okay, so this is just basically showing you how data is actually collected experimentally. So if we take a look at this, this is the initial time, T0. So that's the time that the reaction actually starting. This will be 6 hours later, 12 hours later is 18 hours, 24 hours. This is how much of the peroxide is being decayed, right? So initially we start off with 1 molarity of peroxide, then we get a half a molarity, then we get a quarter, then we get half of that, so on and so forth, right? And then so this represents that change, right? So starting from what we started off with initial, what we lost a half, right? Okay, so and then this is the change in time. So it represents the change in time. And so this would be the decay rate that's given. So that would be the rate that they would calculate it experimentally, right? So you're saying that the rate, in this case, is going to equal that change in concentration of peroxide over the change in time. Okay, this is our rate that's given. These are the concentrations, or the change in concentrations. And this is the change in time. Okay, so then we would use this to sit there and establish what we call a rate constant. Okay, so the rate is going to equal to a constant, K, times this. And so you'd use the data to sit there and calculate what K is. Does that make sense? Okay, I think. Yeah. Okay. Okay, so when we're talking about rates, we have a couple of types of rates to take into consideration. One is the average rate of the reaction. So we're taking it, if it's proceeding over a long period of time, then we're taking the average rate that happened is over that, from beginning to the end of that time period. Instantaneous rate is a rate at a specific time and at a specific concentration. So if we go back, well, this is the rate at, this would be the rate at a 6-hour interval right here, 6-hour interval. Okay, so that would be a rate at a specific time. And this is kind of important because as much as we want to think that the rate is consistent throughout, right? Sometimes the reaction needs to get over a hump, right? So it needs to get over a growth point. Sometimes the beginning of reaction actually starts slow, and then it speeds up as time goes on. Okay, and then it'll level off. Okay. Okay, so let's see. And then we've already talked about the initial rate. Initial rate is when the rate of the reaction at time 0. Most reaction rates at time 0 is going to be 0 because nothing's happening at time 0. Although we may have cases where we've already started the reaction and we're going to say, well, this is our initial rate at this particular time, and we're saying this is 0.0. Okay. So here we have peroxide being decayed, right, into water and oxygen gas. So if you take a look at this reaction, well, this rate over here is quite different than the rate later on, right? So the slope changes quite a bit for this particular reaction. Okay. So in this case, we have two different rates that are happening at a given point. Does that make sense? Okay. So depending on the time that we look at, we have one rate, and then we look at the a later time point, we have a different rate. The change is different. Okay. Okay. So it says calculate the rate, the reaction rate for the decomposition of, let's see, what is that? Carbonate from the following data. Okay, so how would I calculate that? That's right. So I would use concentration, the change in concentration over time. So we'll go. So the change in concentration over the change in time. Okay, so T initial, T final minus T initial, and it's also a negative since it's going to be broken down, right? It's a decay. So then in this case, it would be negative T final, which is 0. I'm going to run out of room. Let me write it down here. So it's negative 0.000 0.880 molar minus 0.0448 molar over 20 minus 2. 20.0 minus 2.0 seconds. Okay. What do you guys end up with? It should be a positive, right? Because this is a negative on the outside. So if you parentheses, yeah. How many sig figs should we have? So we have 3 or 4. Was that 3? That's right. It should be 3. Right. Okay. So what did you guys get? Okay. Okay. Piece of cake. Not too hard, right? Simple, right? Kinetics. Piece of cake. Good. Okay. So you guys kind of you're seeing that relationship, right? So now we're talking about the reaction rate. We can express it as that change over time, right? That change in concentration or pressure over time. And it could be either the change of the reactant or it could be the product, either one. Because you know, if you're getting rid of one, you're going to be getting the other, right? Okay. So we also know that we have to use stoichiometric factors, right? And that's what I was showing you earlier. Okay. So if we take a look here, we have 2 moles of ammonia, and we have 1 mole of nitrogen gas. So the ratio is going to be a 1 to 2 mole. So if we're talking about the concentration of ammonia, right, it's going to be multiplied by 1/2, right? Because we have to do that molar conversion. Okay. It's you can do it the way that they have it here because it makes more sense here. I mean, as using the molarity, because then it gets rid of the units and you can see it easily. So okay, so and this is just basically showing you what is happening in that context. So if we're taking a look, so this is the concentration and molarity. This is the concentration of the ammonia. So as the ammonia is decaying, the hydrogen gas and the nitrogen gas are both going up. Right? Make sense? Oh yeah, I'm sorry. I'm just putting on the screen. Yeah, so as the ammonia decays, hydrogen gas goes up and nitrogen gas goes up. Okay, so given the rate of decrease of nitrogen monoxide concentration, which is 1.60 times 10 to the minus fourth molar molarity per second. Calculate the rate of decrease of oxygen concentration from the given chemical equation. Okay, first thing that we have to do is to do what? Balance the chemical equation. Okay, so is it not balanced, or is it balanced? It's not balanced. Okay, so how would I balance it? Two in front of the NO. So that's 4 oxygens, 2 nitrogens. Does that work out? So you're saying a 2 in front of the O2, NO2. Okay, does that work out? Are you sure? You'll put a 3 on the oxygen? Okay. So 4 nitrogens. That's 4 plus 6. That's a total of 6 oxygens. You guys agree? NO. So that's 4. That's 6. That's 4. That's 6. Okay. Okay, so we know that the rate for oxygen monoxide was, so NO delta T. That's equal to 1.60 times 10 to the minus fourth moles per second. But we want to find the ratio of oxygen, the rate of oxygen decrease, right? So then if we're starting from this, we need to convert to oxygen. So we'll go NO delta T, and this will be moles of NO. So how many moles of NO do we have? 4. To how many moles of oxygen? So then the concentration of O2 would be 4.00 times 10 to the minus 5 molarity per second. Okay. Piece of cake? I don't know my hand's big. Okay. Oh, is my head still in the way? Let's see if this actually works. Okay, so things that affect reactions. Okay, so first I'm going to show you an experiment. See if it works. I know you can't hear anything. He's taking this piece of metal, right? So these are three alkali metals. So that's like sodium, potassium, and lithium. And he's cutting them. He's going to drop them in water. I've done this experiment before. You guys are probably going to do this experiment. That's potassium. I think that one's sodium. Maybe lithium. Why did they put the two over there? Because it can get very volatile. Because it'll really blow. I was in class and I had been in the habit of cutting it and weighing it, and I was being lazy, and I was estimating how much I was adding. You saw that one? That's exactly what happened. And my laptop experiment was right here. Laptop right here. Laptop stopped working immediately. Larger piece, same metal. I think the first one is either sodium or lithium. And then this last one, they put a big old chunk of it in there. So. Did you see that, Marisol? Did it show up on your screen? Your enable?
Yeah.
Okay, good.
Yep.
Okay, so one of the things that affects reactions are the nature of the reactant, right? So obviously, if it's known to be a very volatile reaction, it's going to be a volatile reaction. It's going to be a fast reaction, okay? So another thing that is going to affect it is the state of the subsidized or subdivision of the reaction, okay? So for instance, here we have iron powder. And then here we have a nail, right? Which is just an iron nail, okay? Now, you'll see this reaction, although you can't see it because it's not moving or anything like that. But this reaction is really happening. You see the bubbles and stuff forming and everything like that. And it's reacting with hydrogen chloride. And then here, we're using the same amount of hydrogen chloride, but you hardly see any reaction happening. You see it just on the surface of the nail itself, right? So this helps us understand that if we have the surface, let's say a solid, we put a full solid in there, we're only going to be reacting on the surface of the solid. And so we can't take in consideration the concentration of that solid or the amount of that solid, because we're only going to be affecting the surface. Does that make sense? Where in the case of the powder, it's all grinded up, and so it has more contact area for it to sit there and react. Okay. The other thing that we have to take in consideration, we already talked about, is temperature, right? If it's cold and everything like that, your reaction is going to go slower. But if we increase that temperature, it's going to cause that reaction to increase. The other thing is concentration. So if we only add a little bit of iron powder in there, well, we're going to get a pretty fast reaction. It's going to end pretty fast. But if we have a whole bunch of it, it's going to react pretty, Okay. And then the last thing is the presence of a catalyst. Okay. So the rate. So now the thing about if we have a high concentration, one thing that's affecting that concentration, so if you have two products that are reacting, right, the probability of them colliding is going to happen more frequently in the case of higher concentration than in lower concentration. So let's say if we had one little piece of metal and one little piece of water, right, by the time that they find each other, it'll take forever. But if we have a whole bunch of metal and a whole bunch of water, right, that has a lot of surface area, they're going to be reacting constantly. So that reaction is going to speed up, right? So the higher concentration, you're going to have more collisions, more reactions. Okay, so let's see if this works. Now this is for any type of reaction, right? Yeah. Yeah. So like say we're barbecuing, right? So if we just like one part of it way over here, right? Only that little part is going to be affected. But if we sit there and we try to light the entire thing, right? Then it's gonna, yeah. Oh, I put it on and I forgot to put it on your side. I'm like, why aren't they saying anything? Look at this. This is beautiful. So you guys, this is phosphorus. Phosphorus in the atmosphere. So in the atmosphere, we have oxygen, we have nitrogen, but in that bottle, it was pure oxygen in that bottle. It's the only thing that's in there. So it's concentrated oxygen compared to what we in the atmosphere. So as he takes it out, the flame isn't as intense or as because the reaction isn't bright. The reaction isn't colliding enough with the phosphorus molecules. Okay. Cool. So, and as a direct result, if you glow stick, guys, we've done the glow stick reaction before, right? So you do the glow stick reaction and you shake it all up, right? The more you let it in contact with each other, the more it's going to be consumed, right? So if we continue to shake it, shake, which increases that contact, right? Then the glow stick isn't going to last as long, right? Where if we just crack it and just let it go on its own, disperse on its own, it's going to last a little bit longer. You're still going to have the reaction happening, so your reactants are being consumed as fast. Okay, so this is just a statue. And so it's made up of a carbonate composite, such as like limestone or marble. And so over time, we'll see that weather will actually causes it to break down and deteriorate. And then also because of thermal contractions and all those things are going to play a huge part on that statue. And that statue looks crappy, right? Over time and more over time. And so that's just an example. So time also is going to be a factor in that process. Okay, so these are the factors. So the concentration or the pressure, temperature, the state, and the catalyst, right? So if we have two chemicals that we're adding, both of them liquid, pure liquid, right? And let's say there's an interface that's formed in between them. So if we have two liquids, one on top, one on the bottom, the only place that they're going to react is going to be where? Where they're touching, right? And that's it. And so that's going to limit the reaction, right? So this just tells us, in the case of concentration, it's the proximity of the molecule. So molecules, more of it around, the more of it you have in proximity of each other. Temperature, the amount of energy that's being added onto the molecules. They're speeding up, so the probability of colliding is going to be much greater. The state, that was a case of liquid and liquid versus, let's say, if I have a gas and I'm pumping a gas in there, gas is going to get everywhere and it's going to have a better reaction. And then the catalyst is just, you guys know what a catalyst is? What's that? An enzyme will be an example of a catalyst. All a catalyst is something that speeds up the reaction. And so often what a catalyst does, it causes the chemical or the compound to orient a certain way to make it optimal for that reaction to occur. So it increases that optimability. Or it causes the threshold energy, the energy to get over a certain threshold to be lowered so that it would be over. So again, like if you tilt it, it makes it a lot easier for that reaction to occur, right? Well, it's something to speed up the reaction. Yeah. The catalyst is something to speed up a reaction. That's right. Yeah, because DNA will break down on its own, but it takes forever for it to happen. But as soon as we throw those enzymes in there, boom, instantaneous, right? So, okay. So the rate law. So the rate law is going to be directly related to the reactants or the products. It could be either one, right? But it's going to be related to the concentration, okay? So the rate is going to equal K, the concentration of A to some exponential, and then the concentration of B to some exponential, right? So let me explain to you what this basically means, right? So the X and the Y represents the order of the reaction. So if it's going to be a first order or a second order or a third order or a fourth order or a half order or whatever. So, and that's determined experimentally. It's not going to be determined by, sorry, it isn't going to be determined by the coefficients. And that's everybody's first instinct, okay? It isn't determined by the coefficients, but it is going to be determined by an experimental process, right? And so most reactions are determined by experimental process. And we know that this represents the concentration. So it could either be pressure or molar concentration that we're looking at. And that rate constant is going to be a function of temperature, right? And so if we're kept at the same temperature, we don't have to worry about it. But if as soon as we start changing that temperature, we will change the rate constant, right? And that makes sense, right? So reactions are going to speed up if we increase the temperature, okay? So rates are they're determined experimentally, right? And that's always going to be the case. That constant is going to be temperature specific. As soon as we change that temperature, that's going to change. So, but that constant doesn't change with time, it does change with temperature, okay? And then the concentration of each of the reactants are also going to be dependent on that. The law is going to be dependent on that. Now, sometimes we'll get a case where the reactant is dependent on one chemical and not the other. Okay, and then so you'll start to see that. Sometimes you'll get a case where the constant isn't dependent on either concentration. I mean, the rate isn't dependent on either concentration of either item. Okay, and we'll talk about that here in a second. So the way that you go, the process that you go about determining the form of the rate law. So the very first thing that you're always going to do is you're going to take a look at your initial measurements. So you're going to take a look at the initial concentration, and you're going to compare that to the rate. Okay. And then you're just going to go through and take experimental values that have been taken for each of those different concentration over a given. Okay. So then that's going to help us figure out a couple of things. One, it can help us figure out the order of the reaction. It can help us figure out the constant itself, right? But in other words, you're basically going to solve multiple equations, multiple algebraic equations based upon the number of unknowns you have. Does that make sense? Like, you guys had it? Look. So let me take a step back. Okay. So, so we have this equation, right? So we have a rate for the reaction, right? Now the rate constant. Now this rate is going to be dependent on the concentration, but it's also going to be dependent on the order. So in this case, if we have the concentration, we'll have the concentration at time 1, at time 2, at time 3, at time 4, and then we'll have rates that are going to be associated with those times, right? So then we'll have our rate, and we'll have the different concentrations that are at the given rate, right? So we could take 3 equations. The first one with that very first rate and that very concentration. The second one with the rate, and then we'll keep the concentration the same, but we're changing the concentration, right? So then that allows us to calculate that X and that Y, right? Because those are unknowns. The way that we'll be able to look at those are experimental. Are you with me so far? Okay, so good. So this is what we're going to do. Now, this is how you basically will use this right now. Let me get there. Okay, so here, if we set up the straight law, we have one reactant here, right? So then we said the rate law is going to be equal to, rate is going to equal K times the dinitrogen pentaoxide, okay? Now, the thing is that this dioxygen pentaoxide, we don't know the exponent on this, but they're just telling you that this is going to be a first order reaction. First order reaction basically means that you only have one reactant that you're looking at, and there's only one to the first power. So it's directly proportional to it. Okay. Are you guys with me so far? First order. Okay. So this here is write the rate law for the following equation. If the reactant is a first order with respects to nitrogen monoxide and a first order with respect to ozone. So in that case, you're saying rate is equal to K times the concentration of oxygen monoxide times the concentration of ozone. Both of those to the first order, so it's to the first power. That's all it is. Okay. That's right. So if they say it's a second order reaction to nitrogen monoxide, then we would put a 2 here. It would be squared instead of. sometimes we have to calculate it, and then sometimes it'll be given to you. Like this will be like in a general question. This is just a general, yeah. And here they're providing that for you. Make sense? What was that? So can you repeat that, please? Uh-huh. No, that just means that it's ozone. It's not oxygen. It's ozone in that case. That's just telling us what the compound is. So remember, subscript always means how many you have for that particular. Yeah. Yeah, don't throw out all the stuff that you learned. Now, this is just building up on it. Okay. So, I'm going to give you one. Don't worry about it. It's all great correct to you right now? Is that what you're saying? Okay, so let's go back. Okay, so here's an example. So calculate the order for each of the reactants, the rate constant, and the rate law for the data collected at constant temperature. Okay, so first off, they told us that this is constant temperature, right? So that means that the only thing that's going to be changing is going to be the rate, the concentrations, right? The orders aren't going to change. So if we write our equation, first off, we want to do is write our chemical equation, or our rate law equation. So how would we write our rate law equation? So we would say rate is equal to what? Oops. My pen's not working. Hold on. Let's see why it's not working. Rate is equal to what? To K. So we don't know the order of the reaction. So then we take a look at the concentration of A. To X. And the concentration of B to Y. Make sense? Okay, so now we need to solve for K, X, and Y. We're given the concentrations, right? Are you guys with me? Okay. So if we say we take 2 points where B are the same, different color. Come on. Trying to be fancy here. Oops. Okay, where B are the same, right? Now the thing here is that A is changing. Okay, so the concentration of A is changing. Okay, so then, and we have a change in rate, right? So then we'll write our equations, maybe, if it lets me. So then we have, come on. Too many pins, too many places. So we have our first equation where we have at experiment 1, where we have the rate is 5.0 equals K. We have a value for A, which is 0.100 to the X power. And then we have a value for Y, where Y is, not for Y, for B, 0.1 to the Y power. Come on. I hate that. Y. Okay. So that's going to be one equation. Then we have another equation where we have 45.00 equals K 0.1. Oops, sorry. That should be 3.300 times 0.1 y. Now we know that K times 0.1 y is going to be the same, right? So we could just kind of say that that's a constant, right? Can we not? Okay, so, or we can just, let me adjust this. So we'll have 5.00 over 0.100 y, x equal to K times 0.1 y. And then I can substitute this in for K. Okay, so then I get 45.0. So I'm substituting, this is K01. So I'm going 0, I forgot to put the X here, 0.300x. I'm substituting this in, so then that's 500, not 500, 5.00 0.00 divided by 0.100x. Okay, so then we get 45 divided by 5, which is 9. .00 is equal to 3x. Because I took the 5 over here and I divided it by 45 divided by 5. I should probably keep my sig figs right, 0. Okay, to the x power. So then x must be equal to how much? 3 to the what power will equal 9? 3 to the second power. Yeah. So that's the same thing as saying 3 squared equals 3x. Okay. So then we know that x is to the second power. Okay. So both of those are to the x power, right? So then we have 1.300 divided by 0.100. So then that's 3, right? Yeah. So then that's how I got the 3x over here. Sorry, I'll go slower next time. I skip too many steps. That's my head is just a hot mess sometimes. Okay, so we solve for x. So we know that the concentration of A is a second order reaction. Okay, so now we got to do the same thing for B, right? So we'll do the same concept where we keep A consistent and then we solve for B, right? So if we do that, so then we have A being consistent here and A being consistent here. So we'll take those rates. You guys got it? Yeah. So we'll write this equation. What was that? X and Y don't have to be the same. Yeah. They could be, in most cases, they're different. Okay. So we have 5.00 for experiment 1 is going to equal to this very first equation, K. And now we have a value for X, so it's 0.100 to the second power. And then we have 0.1 to the y. And then for the second equation, we're going to use experiment 3. So we have 10.0 is going to equal K. And then again, it's going to be 0.100 times 0.200 to the y. Okay, so then if we solve the first equation for our y value and then substitute that into our second equation, so then we'll have K 0.100 to the second power is going to equal 5.0 over 0.100 to the y power. It's a horrible y. Okay, so we plug that into our second equation, this one down here. So then we end up with we have 10.0 is going to equal 5.00 over 0. I hate this. 100 to the y power times 0.200 to the y power So then we'll get, it's 10 over 5. It's going to equal 2 over 1 to the y power. So then that means that y is going to equal 1. All right. Okay. So now we've solved for x and y. So then we could just take any of these equations and then solve for k. So let's take this last one here, plug that in. So we'll have so we'll have 10.0 is going to equal k times 0.100 to the second power times 0.200 to the first power. I'm going to erase this over here so that we don't get this confused. And then we solve for k, right? So then we get so this is what squared. So that's 0.001. Oops, let me do the math. Carried away. Eraser. So I'll get k times 0.002 is equal to 10. So then k is going to equal 5 times 10 to the, oops, that should be 3 sig figs. So it's 5.00 times 10 to the third. And so it's based upon concentration. So then it would be molarity. It would be, so for us to have seconds over molarity. So then it would be molarity at the bottom, squared at the bottom, seconds. So 1 over molarity seconds. That will be the units. Okay. That's right. Algebraic substitutions, yes. That is correct. So for us to get moles over liters, it has to be, since we have it cubed, so it'd be, I mean, not moles over liter, moles over seconds. It has to be, the units for the constant would be 1 over moles squared times seconds. Molarity times seconds, yeah. Okay, so let me clear erase. So your answer is right here. Okay, piece of cake? Okay, so let's stop here. My butt's sore sitting down. And I will see you guys tomorrow, mañana.